In this video, we are going to talk about Taylor and Maclaurin series. So the question here is, can we represent any function as a series like we saw in the previous video? Well, one thing that we can do is that we can try to say that f of x, so suppose f of x can be represented the following way. Okay, so let's say you had f of x. This can be represented as c0 plus c1 x minus a plus c2 x minus a squared plus c3 x minus a the third plus blah, 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 provided that x minus a is less than r. So basically what this is, we're representing a function as a geometric series. Okay, so let's just suppose that we can represent it like this, okay? And notice that if I plug in the value of a into x, I'm just going to get c0. Because I plug in a and every single x, everything is going to cancel out except the first term. Now, what is c0? All of your ci's, like c1, c0, c2, c3, these are what we call constants. So these are just constants. We don't know what they are. You know that we have x, a can be any value that we want. Okay, so ci is just my constants, but notice that I can find out what my c values are, at least c0, is if I plug in a into the function. Okay, so this is what I'm going to assume. So what we're going to do now is that we're going to take the first derivative. Okay, so we're going to take f prime. So f prime of x is going to give me, well, that's going to cancel out the z0, so that one's gone. Here, the derivative of x is just going to be 1. The derivative of a is going to be 0. So all I'm going to be left with is c1. Then I take the derivative of the second thing. Using the chain rule, I'm going to get 2c2 x minus a. Then I'm going to get the next one. I'm going to get 3c3 x minus a to the second power. Then if I had another one, it would be 4c4 x minus a to the third power, and so on and so forth. And notice that the radius of convergence hasn't changed. Well, in this case, if I were to plug in a into this particular function, I'm just going to get c1. Okay, so that means if I don't take any derivative, I'm going to get the first constant. If I take the first derivative, I'm going to get the second constant, which is c1. Okay, so what do you think is going to happen when I take the second derivative? Okay, so now what we're going to do is we're going to take the second derivative. So what I'm going to get is f double prime of x. I'm going to take the derivative of c1. That's just going to give me 0. The derivative of this thing is just going to be 2c2. And then I take the derivative of the next term. That's going to give me 2 times 3c3 x minus a. And you'll see why I'm writing it as 2 times 3 in a little bit. The other one's going to be 3 times 4 c4 x minus a squared, and so on and so forth. Radius of convergence hasn't changed. So now what is f double prime of a going to be equal to? Well, f double prime of a is going to be equal to 2c2. Okay, so now let's just do one more. Let's now take the third derivative. Okay, and just for the sake of lack of messiness, I'm going to write it as f3 of x. This will symbolize the third derivative. So we're going to take the derivative of this thing. That's going to go to 0 because that's just a constant. Okay, I'm going to take the derivative of this. I'm going to get 2 times 3c3. Take the derivative of this. I'm going to get 2 times 3 times 4c4 x minus a. Then the derivative of the next one would be 3 times 4 times 5c5 x minus a squared, and so on and so forth, provided that x minus a is less than r. Well, notice now that the third derivative of A is now equal to 2 times 3c3. Okay, and notice that this is just 3 factorial c3. Okay, I'm not going to take the fourth derivative, but you can kind of realize what the pattern is. And here is the pattern. The pattern here is that if I take the nth derivative and then I plug in A, what I'm going to get is 2 times 3 times 4 times 5 times all the way until I get to n, whatever the derivative is. Then I'm going to have Cn. Well, this thing is just n factorial times the constant Cn. So that's the pattern that we've been noticing for all of these things, because this is just 2 factorial C2. This is just going to be 1 factorial C1. Oh, I wonder what this is. Well, this is going to be 0 factorial C0. And remember that 0 factorial is equal to 1. Okay, so you see this type of pattern. So what we're going to do, okay, let's solve for Cn. Because right now what we have is that the nth derivative, and then I plug in A, is going to be equal to n factorial Cn. I'm going to divide by n factorial. And I can actually figure out what these constants are going to be. These constants is going to be, take the derivative, whatever derivative you want, plug in A, and then divide it by n factorial. Okay? All right, so now what does this tell us? Okay, so one little note, I think, if you see f of 0 of A, this just means the original function. Okay, I'm not taking a derivative. Okay, so what this says is the following thing. So this says that if f has a power series representation, or we're also going to call it expansion, at A, some value A, and you can express f of x as n equals 0 to infinity of Cn x minus a to the n power, provided that x minus a is less than r. Notice that this thing is just what we expanded up here from the very beginning, what we assumed. So if I know that a function has a power series representation of this, then its coefficients, so the Cn's, are given by the following formula. Cn is equal to f to the nth derivative of a divided by n factorial. Okay, so which is what we just proved. So what this says, so f of x can be written as the sum from n equals 0 all the way to infinity of f to the nth derivative of a x minus a to the n divided by n factorial. So notice that this initially was this part. I'm just plugging in this thing for Cn, and that's how I got this. And if I were to expand this, what I'm going to get is, well, I'm going to get f of a plus f prime of a over 1 factorial x minus a plus f double prime a to the 2 factorial x minus a squared plus f to the triple prime of a divided by 3 factorial x minus a to the third, plus so on and so forth. So you can see the patterns. X, you first start off with the function evaluated at a value. You continuously take the derivatives. Whatever derivative that is going to be divided by whatever the number of the factorial, and then same thing with the x minus a. They just keep increasing. Okay? This thing, what we just found, is what we call Taylor series. Okay, so sometimes your calculator does it. Whenever you put something in your calculator, it computes a Taylor series of it. So it's a really powerful tool. And you'll see that this Taylor series are used a lot, especially in areas of differential equations. So we do have a special case. And the special case is when a equals 0. So when n equals 0, this special series is what we're going to call the Maclaurin series. Okay, so Taylor series is a little bit more general. It's for any value of a, whereas Maclaurin series, we just want to look at a equals 0. So our function f of x is going to be the summation from n goes from 0 to infinity of f of n, plug in 0 into a, divided by n factorial, x to the n. Notice that the a goes away because when I plug in 0, I'm just going to have x to the n. Okay, so this is basically going to be f of 0 plus f prime of 0 over 1 factorial x plus f double prime of 0 divided by 2 factorial x to the power of 2, and then so on and so forth. So this is what we call a Maclaurin series. Okay, so in the next video, we're going to do some examples of Taylor series and Maclaurin series so that you can get used to them.